Yes, gateway day today. Today's the day. So about the first 40 minutes we're going to have lecture, and then about 40 minutes into it or so we will have you do the gateway. You'll have a half hour. 6 questions, get exactly 5 out of 6 exactly right, no partial credit. I will grade them today. I will not give them back to you, but I will send you your score. If you want to come and look which problems that you got wrong, you can come to my office. I will be there between, let's see, 1:50 and 2:40 or so. I'll be in my office for the most part. Also maybe briefly after 4, but not real long after 4. If you did not pass, if you get less than 5 out of 6, then you'll need to retake equivalent versions with me in my office or near my office at your convenience, and then a time that I can meet with you too, as scheduled times. Anyway, so that's today. As far as topics for the first 40 minutes, essentially it's going to be a big review of what we've done recently, numerical integration and probability, and a little bit of extension, introduction to something called the comparison test for improper integrals. I should mention the improper integrals too. And also the idea of a cumulative distribution function so that you can do a little bit of homework in section 8.7 over the weekend as well. I will be coming up with a Mathematica assignment where you're going to have to use Mathematica to do some numerical integration, but you can just take my code and use that or modify it if needed. Okay, so let's go down here. And once again, we're thinking about this example. Long description there, but again, the main idea is that smaller. You're doing wait times, keeping track of wait times for cars entering intersections. By the way, this wait time kind of example works for other kind of wait times, like wait times in line, other kinds of processes. How long do they take? It's not just cars entering intersections, though that's important. Found out we have another person in the second section whose mom is a traffic engineer and evidently thinks about this kind of stuff. Okay? So we have the exponential distribution, and the function that we used was f of t equals 0.1 e to the negative 0.1 t, and you integrate that function, for example, over the interval from 2 to 7, for example, to find out the probability that the next car will take between 2 and 7 seconds to enter the intersection. I did emphasize, a couple, 2-3 weeks ago, that you can also emphasize the meaning of this by simulation. So here we have the graph of f. This probability density function is the official name for it. Probability density function, or PDF for short. So here's a graph of it. I've got a particular interval. This is the interval from 3 to 10. And when I run the simulation, I get data. Those black dots represent data that I've gotten, that I imagine with my phone, the different wait times. It's simulated data, it's not real data. The idea is the density function simulates data. You can sample from this function, so to speak. Each black dot represents a wait time. And there's a good reason to call it a density, because the points are going to be most dense where the graph is highest. They're going to be most dense where the graph is high and less dense where the graph is low. It's a good idea to call it a probability density function. It's going to be similar to what we're going to see in Chapter 8 with a physics kind of problem that is related to something called mass density. This is probability density. The area of this shaded region is supposed to be the probability that we see between 3 and 10 seconds wait time for the next car entering the intersection. And what that means is, over the long run, about 30% of the simulated data. And the real data, if it's a good model for real life, will be inside that interval I got 100 data points here, and if you do this little bit of code right here, it counts how many data points are between 3 and 10. It should be close to 37 or 38 of them. 35. Okay, we saw that before. Actually, this particular probability density function is just one example of a family of functions that are all probability density functions, no matter what this letter lambda is. That's a Greek letter lambda. Turns out this is a probability density function, no matter what lambda is, as long as it's positive. For t greater than or equal to 0 and lambda strictly greater than 0, this is going to be a PDF. How would you verify that? It's always bigger than or equal to 0. That's one condition you need. You don't want negative probabilities. Another condition you need is the area under the graph over the entire domain must be 1. Said that last time, I emphasized that. The area over the entire domain must be 1. Now the domain is from 0 to infinity. So the improper integral of this kind of function, no matter what this constant lambda is, that would better be 1, no matter what lambda is. Let's see if it is. Always remember when you're doing these improper integral calculations, I want you to put the limit sign in here. When you have an infinity up there, you change it to a b and let b go to infinity. For any fixed positive value of b, this is a proper integral, an ordinary kind of integral. It's the limit that makes it an improper integral, corresponding to the infinity there. This limit may or may not exist. If it does exist, you say the improper integral converges. If it doesn't exist, you say the improper integral diverges. This one is going to converge, and it will converge to 1. No matter what lambda is, your antiderivative looks like that. Think about that for a second. Take the derivative of that function in your mind. You get an extra factor of negative lambda from the chain rule, which would give you that. You could do a substitution if you preferred. Let w equal negative lambda t. dw would be negative lambda dt. And just write down the antiderivative. By the way, on the gateway exam, I should tell you that I only grade your final answers, not your work. So your work could be wrong. As long as you circle the final answer and it's right, then you get it right. Okay? So make sure you circle your final answer. Careful with minus signs here. Sorry it's so loud out there. That's the video too. 2 negatives make a plus. E to the 0 is 1. This thing goes to 0 as b goes to infinity. The limit is 0 plus 1 is 1, and it didn't matter what lambda was. As long as it's positive. Lambda does need to be positive. Doesn't matter. You always get 1. Different lambdas do affect the shape of the graph, and this code that I have right here is going to show you how those graphs change. Let's clear distribution graph. It doesn't like to get redundant. Okay, it's entered. Different lambdas give you different looking exponential decays. But no matter what lambda is, the total area out to infinity still equals 1. So if over here on the left, if the graph goes up, that's going to mean it's got to decrease faster to make the total area still 1. If lambda is high, the fact that this is a probability density function means most of the data is going to be low. By the way, the red dot was the mean, the average of the data. I forgot to mention that. You don't see it here, but in the previous thing, the red dot was the average. If lambda's high, most of your data values are going to be low. If lambda's low, most of your data values are going to be, well, they're going to be spread out is probably the best way to describe that. A small lambda will produce data that is real spread out. Very large t values could occur. Somewhat frequently, you might say. Oh, it's, okay, let's see. This was working on my computer. I think it's still getting messed up by me not clearing things. Let's see if this does it. What else should I clear? Clear distribution graph already. Do I need to do that? Sorry about this. Oh, clear data. Ugh, still not working. Oh, I do have to define distribution graph. Maybe I shouldn't clear distribution graph. Okay, there we go. This one simulates data too. So here's a small value lambda. We're getting lots of relatively high values of the wait times. I make lambda smaller. Most of the data is small. And once again, the red dot is the average of the points. Must be a lot of them here, sort of overlapping. This is why that's so small compared to the highest value. In fact, the red dot, the location of the red dot turns out to be 1 over lambda. Lambda's close to 2 there. That red dot's close to 0.5. There's 5, 4, 3, 2, 1. That's close to 0.5. The red dot ends up always close to 1 over lambda is what happens. Let's try lambda's 0.5. 1 over 0.5, close to 0.5, is 2. The red dot should be close to 2. It is. Not exactly because it's simulated, but it should be close. I can change A and B as well. Get different intervals that I'm thinking about. And the numbers down here, this represents the probability of being in this region. It's the area that's shaded. That represents the count. And these numbers, thinking of that as a percent, 59%, they're always relatively close. As I move the sliders, the data changes, so that's why you see the changes. But thinking of that as a percent, now again, 57% is pretty close to 61. I hinted at the fact that you could use other functions for probability density functions besides this exponential distribution. This exponential distribution is the one that's used for wait times. It's fairly simple. But you could try others and see how they do. I mentioned last time we could try something like this. F of t equals, maybe I should clear F just to be certain I'm not in trouble with that. F of t equals 1 over 1 plus t squared. That in and of itself is not a probability density function, because if you integrate it from 0 to infinity, you don't get 1. What do you get? You get pi over 2. Interesting. Why would you get pi over 2? Oh, the antiderivative is arctangent. Arctangent of t. Gateway help. Plus c. Don't forget your plus c's on the gateway. Arctangent of b as b goes to infinity. The arctangent function's got a horizontal asymptote if you graph it. I don't know if you remember what the graph looks like. It looks like this. It's got a horizontal asymptote at pi over 2. And arctangent of 0 is 0. That's why it's pi over 2. So it's not a PDF, but I can modify it to make it a PDF. Instead of having a 1 over there, up there, have a 2 over pi. Now it's a PDF. Now I can use it to do simulations and compare with data to calculate probabilities. If I want to calculate the probability based on this model that the answer is between 3 and 10, I get a different answer that's given in exact form like that and given approximately by that. With this model, it would take about, be about a 14% chance that the next car would be between 3 and 10 seconds. I could do other models. Okay, you could go hog wild with all these models. Maybe I try 1 over 1 plus t cubed. Not the 32nd power, but t cubed. 1 over 1 plus t squared has a graph that's concave down to begin with and then concave up. So does 1 over 1 plus t cubed. E to the negative 0.1 e to the negative 0.1 t is concave up the whole way. What does this one integrate to? Weird. 2 pi over 3 root 3. So I can make it a PDF by, on top here, putting 3 root 3 over 2 pi. Now it's a PDF. What does this integrate to from 3 to 10? A smaller probability. Yeah, smaller answer. I better not try to guess why offhand here. Is it easy to integrate this function? By hand, is it possible? Turns out it is possible to do, but it's not real pleasant. I think the answer is going to involve maybe arctangent and maybe a logarithm as well. Yeah. Ugh. You wouldn't want to do that one by hand. Numerical integration would be better. But say you didn't want to do that one by hand. How would you do it by hand? You try to factor the bottom. It is actually possible to factor the bottom because it's the sum of 2 cubes. And you get a linear factor and a quadratic factor. And the quadratic factor you'd not be able to factor further. It's called irreducible. And you'd have to do completing the square kind of stuff before doing a trig substitution, probably involving tangent. So that arctangent comes into play. It would be a big mess. But what if you just wanted to know, I want to know if this converges. And I don't have Mathematica to tell me that it seems to converge. What would I do? Well, when, phrase it this way, when t is greater than or equal to 1, t squared is less than or equal to t cubed. So 1 plus t squared is less than or equal to 1 plus t cubed. These are both greater than or equal to 0, by the way. And why am I doing this? If I take the reciprocal of these things, the inequalities switch direction. This one does. This still stays positive. The graph of 1 over t cubed is below the graph of 1 over 1 plus t squared. Did I say that wrong? The graph of 1 over 1 plus t cubed is below the graph of 1 over 1 plus t squared when t is bigger than or equal to 1. Might look something like this. They're equal when t is 1. So this is y equals 1 over 1 plus t squared. This one is y equals 1 over 1 plus t cubed. They switch which one's higher when t is between 0 and 1 because, effectively, because when you square or cube a number, when you square a number between 0 and 1, it gets smaller, and when you cube it, it gets even smaller. You know, 0.9 squared is 0.81. 0.9 cubed is 0.729, it's smaller. So the reciprocals end up being bigger in that case. So you get something like this. The total area under both, well, okay, if I did the appropriate numerators would equal 1. It's not when I don't have the appropriate numerators. Once again, this is y equals 1 over 1 plus t cubed, and this is y equals 1 over 1 plus t squared. Suppose you didn't have your computer technology and you didn't feel like integrating this thing. Could you still be confident you could make a PDF out of it? Could you still be confident that its improper integral from 0 to infinity would converge? The answer is yes, because the graph of this one, when t is bigger than or equal to 1, is below the graph of the other one. So if the area under the other one is finite, therefore the area under this one is finite. That's the idea. And that's the essence of this thing called the comparison test. You can say something like this. The integral from 1 to infinity of 1 over 1 plus t cubed converges since this is true. Let me just put an arrow. Pointing from these inequalities down to here, indicating you should write that in there. For t greater than or equal to 1, and since we know the improper integral from 1 to infinity of 1 over 1 plus t squared converges. Notice I am starting these integrals at 1 instead of 0 because that's where the inequality is true. I should have emphasized that up here. For t greater than or equal to 1. So over this interval, at least, from 1 to infinity, you can say this improper integral converges. Even if we can't find the limit will exist because you know these inequalities are true, and because you know the integral of that one converges. In fact, it would converge to pi over 2 minus arctangent of 1 instead of arctangent of 0. Arctangent of 1 is pi over 4, actually. That's arctangent of 1. It actually converges to pi over 4. Knowing that it converges to pi over 4 is not a big deal in saying this converges. The key thing is that this integral converges, not knowing what it converges to, and this fact. You can say, once you know this converges, by this comparison test to this integral, and because of this fact, you can say that it does converge to something less than pi over 4. So it's relevant as far as estimating its value. I'm not being real formal here. I could write this up as a real formal proof with sentences, but for sake of time, we got the gateway today. I'm just giving you the basic idea. I will tell you, I will want you to eventually write these up as sentences. In fact, on a homework problem over the weekend, I will want you to write sentences. I will create a new example for you, or maybe even this example, and I'll write it out in sentences and make it available for you to kind of mimic. When you use the comparison test in a formal way with a proof, essentially, you should write sentences. But this is the basic idea. And I will tell you, the most common mistake people make is they don't put the integral signs in there. They just say the function converges. That's not the issue. The issue is, does the improper integral converge? As a final comment, before we go on to one new example and then the gateway, is, so this is related to this integral from 1 to infinity. We really want the integral from 0 to infinity. But that's no problem, because the integral from 0 to 1 definitely is a finite thing. It's not an improper integral like with a vertical asymptote there. There is a positive value that's not infinity, so to speak, for that function right there. The area from 0 to 1 definitely is finite. So you can say, in fact, that the integral from 0 to infinity also converges. Okay, so again, I'm not writing a formal argument here, just trying to give you the idea. Comparison test can help you be confident that an improper integral converges or diverges. There are examples like that. And therefore, you can be confident in approximating it, even if you don't know how to take the antiderivative. Or even if the antiderivative is nasty. Okay? If you don't have your technology. Of course, once we've got our technology, you can do this kind of thing. Let's see what it equals. Not too bad, actually. 15 minutes thinking away. Okay. Let's continue emphasizing improper integrals and also emphasize numerical integration. Probably the most important PDF, probability density function, is for something called the standard normal distribution, or just normal distributions in general, but we're just going to do one example, the most common example to think about. It's this function right here. You might want to write that down. That's the PDF, the probability density function, for something called the standard normal distribution. Standard normal PDF probability density function is this function that you see here. 1 over square root of 2 pi e to the negative x squared over 2 power. Turns out this is a PDF over the entire real number line. That's the domain we're thinking about here, is the entire real number line. And where does the 1 over square root of 2 pi come from? It comes from the fact that this improper integral, where you have a minus infinity and a plus infinity involved, ends up equaling square root of 2 pi. That's why you put the 1 over square root of 2 pi there, to make the area under this function forever, well, under this function, forever equal 1. Forever, I mean in both directions. The graph of this is the so-called bell-shaped curve. Looks about like this. It's centered on 0, and its inflection points are at 1 and negative 1, it turns out. Drawing. Areas under this thing are very important in applications, to statistics, for example. In statistics classes, you use this distribution, this probability density function, all the time. Though if it's not a calculus-based stats course, you use your calculator or tables to find areas under this function. You don't really worry so much about the formula. It is an improper integral, though. We need to know it converges. Briefly talk about the idea of why it converges. You could use the comparison test, ultimately, and is something you'd want to use because if you try to find the indefinite integral of this function, it's not an elementary function. It's not something you're used to. Oops, gotta update the function. I should put this above the other one anyway. It's not an elementary function. What? I didn't enter that. Earth. What? Earth? Yeah, Earth. Just a function you've never heard of. Earth stands for error function because normal distributions model errors in experiments, for example. Measurement errors. That's why it's called the error function. So, we need to approximate areas under this thing, and the way you approximate it is with numerical integration. So let's think about numerical integration in the context of this function. And emphasize what we've learned about numerical integration, and something new as well. So the setup here is similar to what I showed you in the last class. We're going to integrate from a to b. I'm going to pick a to be 0, b to be 2. Calling it delta x now instead of delta t. T was thought of as being time. X is just going to be thought of as being a variable. That's common to use. Delta x is the width of each subinterval. It's the length of the entire interval, b minus a, divided by the number of pieces, n, the number of subintervals. That should make good intuitive sense. It does depend on n. This is x sub I, the right endpoint of the ith interval. So when I is 1, it's x1, it's the right endpoint of the first interval. When I is 2, it's x2, it's the right endpoint of the second interval. When I is 7, it's x7, it's the right endpoint of the seventh interval. It depends on I, but it also depends on n, so I put that dependence in here. Left-hand sum, right-hand sum, trapezoid, midpoint, and Simpsons. You're real comfortable with left-hand sum, right-hand sums, and trapezoid sums. The new ones were mid and simp. Remember how the midpoint one is done. You're still taking rectangles, but this time you take the midpoint of the subinterval and use that to go up to the graph to determine the height of the rectangle. F of the midpoint is the height of the rectangle. This quantity inside here is the midpoint of the ith interval. X sub I minus 1 in written notation plus x sub I over 2. In I is 7, for example, this would be x6 plus x7 over 2. Halfway between x6 and x7. Then we saw that, looking at the errors, that the midpoint rule does about twice as good as the trapezoid rule, at least for fairly large values of n. So it makes sense to define a new rule to give the midpoint rule twice the weight. It's a weighted average. The midpoint rule gets twice the weight than the trapezoid. This is a weighted average of those. You got to divide by 3 because it's like you got 2 versions of the mid and then the trap. They did tend to actually also have opposite signs for the errors as well, for large values of n. So this is a good idea. It's called Simpson's rule. Simpson's rule can be approached from a different perspective. I think it's actually based on quadratic approximations to the graph. We're not doing that. Our book is taking what you might call an experimental error-based approach, looking at those errors and approaching Simpson's rule based on what we observe. Let's spend the rest of the time here before the gateway, down to about 7 minutes now, looking at these errors again. So we want to approximate the area under this PDF from 0 to 2. That's going to mean we're wanting to find the probability that a data value that you're going to observe will be between 0 and 2. For some experiment where this standard normal distribution is a good model. Okay? And again, because that was called the error function, one area where you see this kind of behavior, normally distributed data, is with errors in experiment. When you make measurements of various physical quantities, whether they be lengths or areas or concentrations of chemicals or forces, you're going to make mistakes. You're going to be slightly off because your measurement instruments are slightly off and because you are slightly off. Now, you don't want your measurement instruments to be biased, to be consistently off in one direction. You want both the measuring instruments and your measurements to be sometimes too big, sometimes too small, random errors essentially. That's the kind of situation where the normal distribution of bell-shaped curve models data, when you've got data about errors. Okay? Now actually it's a little funny because in real life you can never really know what the exact error is because you cannot know what the exact value is. But it's reasonable theoretically to model with a normal distribution.
I'm just wondering if you're going to give us any time for a midway exam or should I go back from now?
Oh, okay. Just hang on. Just a couple more minutes. Okay. Let's just look at these errors again. I've also got what I call the most precise probability using n-integrate. Probably n-integrate uses Simpson's rule for a fairly large value of n to get a real precise value. So let's compare these things. Remember that the error is the actual value minus the approximation. The most precise probability thing is going to be the most precise estimate of the actual value. When I subtract the approximations, for example, from the left-hand sum, I get the error. That difference is negative. That means the left-hand sum's too big, actually, because when you do the subtraction, if you subtract something too big, you're going to get a negative number. Will the right-hand sum produce a positive error? It should, because this graph is decreasing from 0 to 2. Looks like that. The right-hand sum is going to be too small. The rectangles are going to be under the curve when the curve is decreasing like that. Positive error. It's a little less clear what's going to happen with the trapezoid rule because the graph is both concave up and concave down over the interval from 0 to 2. Over the interval from 0 to 1, it's concave down. But over the interval from 1 to 2, because that's an inflection point, it's concave up. So it's hard to say whether the trapezoid error is going to be positive or negative. It's positive. The trapezoid estimate here is a little too low. Will the midpoint one be negative then? I'm not sure. Though I think if I increase n, they will have opposite signs. Change trap to mid. Ends up having the opposite sign, and it is about twice as close to 0 as the trapezoid one. And then probably Simpson's rule is definitely, well, definitely it's the best, I'm sure. Real close to 0. Okay, for the error. Doing these things would give you the actual approximation, which we're not seeing here. I guess I suppose I should do that. Just a second, give me a minute. Oh, come on. Stop. Oh, why is it doing that? I didn't do italics. I think at least. Oh, come on. Maybe it's got to do with the slash. Okay. Evidently, the answer is close to 0.477. The only new thing I want you to see here is watch what happens when I increase n by a factor of 10. Okay? So I'm going to change all these 2's to 20's. What do I predict is going to happen? It's a fact stated in your book that if you increase n by a factor of 10, you get about 1 extra digit of accuracy with left-hand sum and right-hand sum. I predict these errors are going to go down by a factor of 10, or yeah, approximately 10. So I'll get 1 extra 0. For every, when you increase the amount n by a factor of 10 to the midpoint of the trapezoid rule, you get 2 extra digits of accuracy. So I should expect 2 more zeros with these 2. And with Simpson's rule, if you do 10 times the work, you get 4 extra digits of accuracy. So I should expect 4 more zeros with this one. I got 4 zeros there after the decimal to begin with. Yep, 1 0 there. Now 2 more zeros on these. This is 4 more zeros because with 10 to the negative 9 power, after the decimal, you'd have 8 zeros instead of 4 before the first non-zero digit. That was quick, I know. I'll re-emphasize that next Monday. Let's take the day away.